The formula for butane was C4H10, all right? And butane, which is 4 carbons in a row, is definitely one of the structures for it. But the problem with the formula, C4H10, is that you can make an isomer of it. And an isomer, same number of carbons and hydrogens, same formula, but it's structurally different. So notice the structure to the right. It's a 2-methylpropane, all right? And that also is 4 carbons and 10 hydrogens. However, as you can see, the structure is quite different. So what we need to talk about before we go any further in organic chemistry is the idea of the longest chain of carbon atoms, all right? Notice that in the structure on the left, we have 1, 2, 3, 4 carbons in a row, in a chain, all right? So the longest chain of carbon atoms there is 4 carbons, and 4 carbons is butyl, which would be butane, okay? That's where that comes from. If you just have carbons in a straight row, then it gets the N symbol. N stands for normal. So N-butane would be the 4 carbons in a row with hydrogens all around. N-pentane would be 5 carbons in a row with hydrogens all around. The structure on the right, if you think about the longest chain, quote unquote, you're going to get 3 carbons, 1, 2, 3. And so this has a longest chain of 3 carbons, which is a propane. And there is a methyl group off the second carbon. Remember that methyl is CH3. So this compound is 2-methylpropane, where the longest carbons are 3. A methyl group is not part of it. That's where these names come from. Now, you don't have to count 3 carbons like I just did there in the nice line. Maybe you looked at it as 1, 2, 3. That's another way to see the propane group, and the methyl group, which is the part I didn't circle, is on the right off the second carbon. So notice that you can get 2-methylpropane from this way of circling the atoms as well. And this is going to be an important trait for you to do. And finally, you could also circle the 3 carbons right there. That would be another propane. The methyl group is off the middle, or the second one, second methyl. So that would also be 2-methylpropane. As an organic chemist, you need to start thinking about how to find the longest chain of carbon atoms, all right? And I would try different ways. So initially I had them all along the axis right there, if you will. Then I kind of twisted them in the L shapes, and that's good to do. You should kind of think about this. The longest chain in organic chemistry is super important, and we'll talk about this more here in a little bit. So isomers is one of the ways that organic chemistry is quite different from the Chem 221 through Chem 223 series of classes. This is something that's not usually talked about that much, but I wanted to bring it up because this is something you will absolutely see both in the regular class and also in the real world. Pentane is 5 carbons, a pentyl group with a hydrogen on the end. And if they're all in a row, then you get to N-pentane, which we're going to start using now because there are isomers of pentane. Now, the formula for pentanes, N-pentane, C5H12. So all these 3 structures have 5 carbons and 12 hydrogens. But you can tell here that they're quite different, all right? So, for example, down here in the lower left, you have, depending on how you circle it, you're going to have 3 carbons in a row, the longest chain, which is propane, all right? And not circled in that chain, there's a methyl group, if you will, above and a methyl group below. So there are 2 methyl groups there. That would be a dimethyl propane. And the numbering, which we're going to talk more about here in a little bit, we're going to put numbers next to both of the methyl groups. So that would be 2,2-dimethylpropane. And we'll talk more about numbers. The one in the upper right definitely needs a comment. So first of all, the longest chain of carbon atoms is 4. And what I'm going to do is I'm going to circle these 4 right here. So that would be the butane part, the longest chain. And you can include the one above if you want to, it doesn't matter. But notice the name. If you count left to right, it would be 1, 2, 3. The methyl group would be off the third carbon. So it might be tempting to write it as 3-methylbutane. However, if you start and count right to left, this would be 1, this carbon would be 2, 3, 4. So we have a choice here as an organic chemist to call this 3-methylbutane or 2-methylbutane. And in addition to the longest chain of carbon atoms, in organic chemistry, you always want to use the smallest number possible. So 2-methylbutane is the official name for this compound. If you said 3-methylbutane, organic chemists would look at you like you were saying something like, I ain't knowing what's going on. Like you know what they're saying, but it's so slangy and kind of lame. And anyway, in the official chemistry world, the smallest number is the way to go. So 2-methylbutane is the official name. Can they figure it out if you say 3-methylbutane? Absolutely, but the smallest number is big. So let me reiterate the importance of these last 2 pages here. The longest chain of carbon atoms, definitely important. And the second thing, smallest number possible.
Hexane is a covalently bonded molecule consisting of 6 carbon atoms and 14 hydrogen atoms. Each hydrogen atom forms 1 covalent bond, and each carbon atom forms 4 covalent bonds. These 20 atoms can be rearranged into 5 different compounds called structural isomers, each having slightly different properties. Notice how the boiling points of each isomer changes. Arranging the carbon atoms in a straight chain produces N-hexane. Moving the end carbon to the second carbon position and rearranging hydrogens produces 2-methylpentane. Sliding the methyl group to the third carbon position produces 3-methylpentane. Moving the methyl group to the fourth carbon position appears to make 4-methylpentane. But wait, rotating the molecule shows that it's identical to 2-methylpentane. Now, adding the end carbon to the second carbon position produces 2,3-dimethylbutane. Moving the methyl group to the second carbon position produces 2,2-dimethylbutane. Sliding both methyl groups to the third carbon position appears to make 3,3-dimethylbutane. But wait again. Rotating the molecule shows it's identical to 2,2-dimethylbutane. These are the 5 isomers of hexane.
Isomers become incredibly important as organic chemistry gets a little bit more sophisticated. All of these 5 compounds are C6H14, so N of 6, N times 2, 12 plus 2, 14 hydrogens. So they're all C6H14. However, you can see that their boiling points were actually quite different. That has to do with polarity and things that we probably won't talk about as much in this class, but there are a lot of differences. So they are not the same compound. They do have different reactivities, and knowing which one it is really important. So one of the goals you should start having is being able to figure out how many isomers there are, and that's what we're going to start talking about and also look at in the organic chemistry lab. Remembering that longest chain, smallest number is really important. Up there in the upper left-hand corner, you can see an example of how this works out. So let's say that you were trying to name this compound. All right, no problem. You first want to circle the longest chain of carbon atoms, and you can see what's done. It's kind of started on the upper right-hand corner and then kind of twirled around underneath. You could have also started on the left-hand pan-methyl, went to number 2, and then 3, 4, 5, 6, etc., etc. The goal, though, is to find the longest chain of carbon atoms. That's going to be the base. So because the longest chain of carbons is 6, that's going to be a hexane. But not in the hexane part that's circled is a methyl group. So now we have to think about the number that's going to be in front of the methyl hexane. You want to use the smallest number possible. So if you start at number 1, obviously you can see it's number 2, so 2-methyl hexane. However, you could also start at carbon number 6. You could say, all right, this is 1, 2, 3, 4, 5. You could also call this 5-methyl hexane, but that would be incorrect. You want the smallest number. 2 is smaller than 5. So this is where it gets really important. Longest chain, smallest number will help you get through organic chemistry a lot. So again, if you see a formula, you want to start by finding the longest chain of carbon atoms. And I would just circle it. And you can just go in one direction. You can't go backwards or anything like that. You want to circle as many as you can because that's going to be the base part of your name. Then you want to number the chain from the end nearest to the first substituent encountered. Substituent would be like the methyl group right there. And honestly, when you're learning, I would number it both ways. So you can see in the picture there, the numbers that were already there, 1, 2, 3, 4, 5, 6 are good, but count it from the other way because sometimes your pictures will be deceiving and it's easy to miss out on a smaller number if you don't count both ways, especially when you're learning it. The substituents that aren't part of the longest chain you put in front and they'll have numbers next to them, and the numbers relate to where they're connected to the alkyl chain, to the longest chain of carbons. So it's 2-methyl. And of course, if you have more than one, you can use a dimethyl, but each methyl group would have its own number. And if there is like a chloro and a methyl, you want to alphabetize because that's how chemists roll and stuff. So here's one that's a little bit more exciting, and you do want to list them alphabetically. So here's another molecule. Might say, hey, how would you name that? And again, the goal is to find the longest chain of carbon atoms. So if you do this, then the longest chain is this way. Technically, you could, I suppose, have something like this, but your naming would get really ugly that way. So as a practical point, I would recommend doing the lower one stuff. So I'm going to erase that. But anyway, this is a 7-carbon chain. Heptyl becomes heptane when it comes to an alkane. All right, so this is going to be a heptane base. And then in red there, you can see the different parts that aren't in the heptane ring. There's a methyl here, a methyl here, and a methyl here. So it's going to be 3 methyls or trimethyl. And CH2CH3 is an ethyl group. So ethyl comes before methyl, and you want to use the smallest numbers possible. So you can see right here, it would be a 3-ethyl, and then it would be 2, 4, 5 trimethyl heptane. Now, I would always, again, especially when you're learning, number it the other way and just make sure that you get the smallest numbers. So instead of 7, we could call this 1, 6 would be 2, 3, 4 is the same, 5, 6, 7. So instead of the name that's given, you could call it a 5-ethyl, and instead of 2, 4, 5, you would have 3, 4, 6. So you can see that there are smaller numbers in the name that's given, and that's why that's a better name here for this. 3-ethyl 2,4,5 trimethyl heptane is the better name than quote-unquote 5-ethyl 3,4,6 trimethyl heptane. Again, the chemists can figure it out, but it's kind of like slang, and I'm trying to teach you the right way to do it. So when you get your PhD from MIT or something like that, you can stand proud, you know. These are the things that keep me up at night as an instructor. But anyway, just put them all together, list them alphabetically, good to go. Let's say that we wanted to name this organic compound. All right. So first thing, figure out what the longest chain of carbon atoms is. And I mean, you can play with this, and I encourage you to circle things and stuff like that. But let's say you were starting out and you're like, oh yeah, no problem. This is the longest chain, 3 carbons. It's some kind of propane. Well, no, because that's not the longest chain. If you look, you can get a longer group of carbon atoms by circling these 4. And again, I circled the ones in the middle of the molecule, but you could also take the top one instead of the far right one, or the bottom one instead of the far right one. You'd have the same thing. So 4 carbons is a butane, and you have 2 methyl groups, 2 CH3s, not in the longest chain that I circled. So this is going to be a dimethyl butane, all right? The question now is, what's the numbers in front of them? Because the numbers are really important as well. If you start on the left and go right, which is what people in America do, because that's how we read, right? 1, 2, 3, 4. It looks like those 2 methyls are off the 3rd carbon, so you could call it a 3,3-dimethyl butane, all right? But again, you should absolutely double check and make sure that the other way of counting isn't better. And so what you can do is go 1, 2, 3, 4, and lo and behold, if you count right to left, it's a 2 carbon, so it would be 2,2-dimethyl butane. So when there's a choice between 2,2-dimethyl butane and 3,3-dimethyl butane, that smallest number always wins out. It's going to be answer B. So again, hopefully you're starting to see how this works. You circle the longest chain of carbon atoms, that's going to be the base, and then figure out the parts that aren't on the base, and you want to put them alphabetical, and definitely make sure you count both directions. 2,2-dimethyl would be a better name than 3,3-dimethyl. Also important in organic chemistry is being able to create a structure from a name. And at first, the names in organic chemistry can be kind of a trip. So let's go through an example. Let's say that I asked you to provide the structure for 2,2,4-trimethylpentane. And of course, that name is kind of crazy and stuff. And at first, it might be like, oh, it can't be done. Oh, trust me, it can. So anyway, let's see how you do it. So the first thing you want to do is you want to go to the end of the name. So in this case, that would be pentane. And pentane, as we talked about, is a 5-carbon alkane. So what I would do in that case then is literally just write with carbons. I would write carbons in a row. And you can see there what I did. I went 1, 2, 3, 4, 5 carbons, all connected by a single bond. Single bonds, of course, being more probable. I also put down a numbering system. Now, I usually read left to right because I am an English speaker. You could do right to left. It's not a problem. Either way is okay, but just make one system and stick with it. So I'm going to use 1 on the left and 5 on the right for this name. Now, before the pentane, there's a tri and there's a methyl. So you can see I'm kind of going right to left in the name. So tri, of course, is a Greek prefix for 3. So that means there are 3 methyl groups in addition to our pentane chain. Now, each methyl group is like a carbon. And to know where you put those 3 methyl groups, that's where the numbers come in. And notice there's a 2, and a 4. So we have 3 methyls total. That means that we're going to have 1 methyl group off the 2nd carbon. We're going to have a 2nd methyl group off the same carbon. Remember, carbon can have up to 4 bonds. Normally, it's populated with hydrogens, but in this case, this carbon is totally surrounded by other carbons. And then, of course, the last 4, we're going to put a methyl group right there. So 2, 2, 4 means put a methyl group in this case at each of those positions, 2, 2, and 4. And tri means 3 methyl groups. You could also have a 2,2,4 trichloro and put chlorines up there, something like that. But hopefully you get the idea. And then finally, if you'd like to, you're welcome to populate the remaining positions of carbon with hydrogen. Again, the name of the game is that carbon always wants to have 4 bonds total. So the ending carbons there definitely would have CH3s. This structure right here is a mixture of some hydrogens and atoms listed, as well as line structures. But again, you can see there's carbon number 1 right there. Carbon number 2 has the 2 methyl groups. Carbon 3 in the middle, 4 right there at the vertice, and 5. So good to go. So that's how you do it. It's pretty chill. Going right to left has helped me out quite a bit on these for what it's worth. Let's do an example of how this all works out. Here's an example where I'd like you to draw the structure 2,3,4 trimethylpentane, okay? And the answers are just silly, so don't worry about that. But again, what you would do, and try this yourself, you would start on the far right. This is another pentane, so that would be a 5-carbon system. And you would literally just write 1, 2, 3, 4, 5 carbons in a row. And then because you have numbers associated with this molecule, I would highly recommend numbering them. So I'll just go 1, 2, 3, 4, 5. And again, you could go right to left. It's no big deal. Trimethyl, again, means 3 methyl groups. But you can see the difference here is that these carbons now are of the second, third, and fourth carbons. So 2,3,4 trimethylpentane is actually different than 2,2,4 trimethylpentane, which we saw earlier. So this is the compound for 2,3,4 trimethylpentane, a little bit fancier than the version I drew, but same idea. And again, the name of the game, start on the far right at pentane in this case. That's the 5 carbons. If it was hexane, it would be 6, etc., etc. And I do recommend numbering them. Number them, and you'll use that numbering system then to find what doesn't fit in the longest chain. So in this case, that was 3 methyls at 2,3,4. In the previous example, 3 methyls at 2,2,4 should be no problem. Alkanes are essentially straight carbon chains, like you have just carbons in a row, but there's like, if you will, a beginning and an end. But there's nothing that says you can't take those end carbons and put them together because they're all tetrahedral. So you take off some hydrogens and make essentially a cyclic compound. So a cycloalkane is nothing more than an alkane with the end hydrogens pulled out, and you put those 2 carbons together. So you can see the different ways here that these things can be done. The simplest one is cyclopropane. So propane had a CH3, CH2, CH3. Well, if you take a hydrogen off the end carbons and make a triangle out of it, that becomes cyclopropane. And notice there the structure. This is very common in organic chemistry, where the vertices and the lines are where the carbons are, and you can see how there's lines to carbons showing, but the hydrogens are totally omitted. And this is very common in organic chemistry, and we'll see that more and more. So a triangle is also the symbol for cyclopropane. And you just have to realize that at each one of those vertices, you've got a carbon. Carbon always has to have 4 bonds. So because those carbons only have 2 bonds, 1 to each carbon, that means there's going to be invisible hydrogens off each one of them. So this is something else to get used to in the organic chemistry symbolism. The one to the left of that is cyclopentane. Again, pentane without the hydrogens on the end. And then cyclohexane would be the hexane without the hydrogens. And you can have cyclobutane and cycloheptane, etc., etc. Notice that the formula for cyclohexane is different than the formula for a regular alkane. A regular alkane was CnH2n plus 2, but because we've removed 2 hydrogens to make the cyclic compound, a cycloalkane is just CnH2n, and that can be kind of important for the things that are going on. So if someone gave you a formula now, you could, in theory, at least tell the difference between a cycloalkane and an alkane based on just the formula. So going back to the list we saw earlier, which of the following could be a cycloalkane? And again, the goal here is to find formula combinations where for every n carbons, you see 2 n hydrogens. So again, number 3, which was the answer for the previous problem, would not work here, because if you had 14 carbons and it was a cycloalkane, you'd expect to have twice that number, or 28 hydrogens. 30 hydrogens is too many, so that's not going to fly. And C7H8 doesn't have enough of anything, so that's not going to happen. There's no oxygen yet, so we can cancel out that one. However, the ones on the left, all right, it's not impossible because you have, for example, in the first one, 2 carbons, so 2 times 2, 4 hydrogens. That's possible. The second one, N would be 5, so 5 times 2, 10 hydrogens. Both 1 and 2 fit the formula for a cycloalkane. However, if you're going to have a cyclic compound, all right, you have to have more than 2 atoms, all right? You can't make like a structure with a circle. You only have 2 points. You need 3 points to make a cycloalkane. The smallest cycloalkane is a cyclopropane with 3 carbons. C2H4 is not a cycloalkane. It's something different. So the only one that really follows the structure here is B. You could have a cyclopentane. Absolutely, that would work. But you can't have C2H4. There's not enough carbons to make a cyclic compound. All right, you would have just a line, and that's not the same as a cyclic compound. Cool. Instead of putting a hydrogen on the end of an alkyl group, you can put a halogen on the end of an alkyl group as well. And that creates another family of compounds or class of organic compounds called an alkyl halide. And an alkyl halide is just an alkyl group with a halogen on the end. And so in this case, you'd have the generic symbol Rx, and X could be fluorine, chlorine, bromine, or iodide. So here's just some examples of how these things work. The first example there, if you had a methyl group and you put an iodine on the end of it, you'd still have tetrahedral sp3 carbon at 109 degrees, but you've got an iodine there. So in the old school way, this would be called methyl iodide, i.e. alkyl halide, so methyl group iodide, and that's fine. Sometimes, though, you'll also see this compound listed as iodomethane, and this is another thing we're going to see in this section. So CH4 is methane, and if you put an iodine on the end, it would be iodomethane. So methyl iodide and iodomethane refer to the same thing, and on a quiz or exam, you have 2 possibilities to win. Woohoo! You could call that methyl iodide or iodomethane, and I would be totally happy. The next one there, you've got 1, 2, 3 carbons, so it's a propane, and you have an iodine I off the middle or second carbon. So the one way to call this would be 2-iodopropane, where the 2-iodo means there's an iodine off the second carbon in a propane group. You could also call this 2-propyl iodide, which is the old way. And again, if you change the iodine for a bromine, you would have 2-bromopropane. And if you put chlorine in there, it would be 2-chloropropane. So there's lots and lots and lots of possibilities. These types of compounds show up a lot in organic chemistry, so you'll see them, and you will see both ways of naming them, so just FYI. But in our Chem 222 class, where we're just introducing it, I'm happy with either way. You're good to go. Does this rag smell like chloroform to you? I put this on here for a silly joke. So the chloroform is what people sometimes use to knock someone out, and chloroform is an alkyl halide. It's CHCl3. So again, my weird sense of humor is popping up again. But anyway, chloroform, if you've ever seen, like in the old black and white movies, sometimes they put this rag over your face, then people go, oh, and they fall, they go unconscious. All right, well, anyway, it's chloroform, trichloromethane. I know, get a life, Michael.